Let's look at two quick examples of using Moxie to execute SysML architectures in the mission environment. This diagram shows your SysML authoring tools on the left and SDK on the right, where design reference missions are modeled that provide the consistent source of mission requirement truth throughout the product lifecycle. In the middle are Moxie and Model Center, which connect your virtual operating environment with your SysML designs. So if you take the concepts here of how this data flow works and apply it to a particular use case, in this case, a very simple one chart kind of level of fidelity example of a communication satellite that we're designing, you would first take the mission requirements that have been levied on you for your particular system and model them in SDK as design reference missions. So these would serve as the authoritative source of mission requirement truth throughout the product lifecycle. And a couple of neat things about that modeling that can go on in SDK and TTK. First of all, you can choose the level of fidelity that you choose to model each of these elements at. So depending on your particular analysis requirements, you could do just a very simple model, or you could do a very detailed model all the way down to, say, ANSYS level physics. The other element of the other choice you get to make as you model these different elements of the system is you can choose which elements are modeled with SysML and which are not. So in this particular use case, as we look at a communication satellite, let's say you might want to model the data caching behaviors that are going to go on in your satellite when it's in a COM degraded or jammed environment. So once you have your system modeled, you'll look at maybe Model Center, MBSE, or a tool like that to run trade studies on the physical characteristics of your system. So for example, let's say we have a requirement in an operational environment such as this to have a certain gain threshold to allow communication between this UAV through the satellite down to the ground station. And through iteration, through trade studies, you might find that particular designs of the sat or the antenna on board that satellite don't provide that minimal gain threshold. So you could iterate, you could revise your structural and parametric aspects of your SysML design system such that you can achieve the physical characteristics to allow you to meet those gain threshold requirements. Moxie, on the other hand, is looking more at behavioral analysis. So for example, let's say you have a requirement to be able to cache up data received from the UAV on board your satellite and then pass it back down to the ground station after some COM degradation criteria have degraded. So you might have a SysML state machine defined that represents your caching behaviors, and you might have a certain suite of memory defined as a structure in your SysML system. So when you execute those structure and behavioral diagrams through Moxie into this mission environment, you might find that, hey, the way this plays out from a timing perspective with regard to where things are temporally and how long the jamming occurs, that I run into a situation where my onboard memory is getting filled up and I can't adequately achieve the COM relay requirements that I have in that jammed environment. So you might go back and modify your memory structures, or you might go back and modify the behaviors, the sequence at which you do your data caching, such that you can rerun your structural analysis and your behavioral analysis through Moxie into this mission environment as modeled in SDK, and realize that based on the modifications you've made, that you can indeed cache up all the data that you needed to in memory and then pass it back down to the ground station after a particular COM degradation situation has resolved itself. So now let's shift gears and look at a totally separate example. In this use case, we're going to model an air vehicle and a radar warning receiver on that vehicle with SysML, and then we're going to use Moxie to analyze how that particular system behaves in a particular mission environment.
Hey there everyone, Mo Syed here with AGI and ANSYS company. I'll be giving a quick walkthrough of the Moxie interface as it stands right now. Okay, so first things first is just a little backstory on this example. This example will include a UAV attempting, or rather a hypersonic unmanned vehicle attempting to fly towards a target to strike. The one problem that it is facing is that there is a Red Force ship in the way, and this hypersonic vehicle has to reach this target without getting in the detection zone of this Red Force ship. So Without Moxie, the main way one would do this in SDK is simply by making a route and then explicitly putting waypoints around the certain detection zone of the red force to ensure that the hypersonic vehicle does not get detected. But now with Moxie, we instead are going to be leveraging these executable architectures and these state machines to ensure that the UAV has the behavior to kind of go around and strike the target. So as you can see here, we have things such as a radar warning receiver state machine that's basically allowing the hypersonic vehicle to detect if there is any type of radar warning that is going on and if it's being detected or not. And then of course with the radar warning receiver, once the hypersonic vehicle does detect that there is some type of radar that is looking for a blue force entity, such as itself, it will then go ahead and decide if it needs to go through some type of evasive maneuvers of either evading right or left to kind of go around the detection zone, or if it's out of the area of risk and can just fly to the target. And of course, it goes through the whole verifying the safety. And here we can see kind of the SysML side of things, where we're able to take a look at the block diagram as a whole of the various systems that are being put together. Now, one thing to note about this iteration of Moxie is it doesn't really have a front end, and currently it's interfaced with Cameo as a SysML tool. But you really can see that Moxie is kind of in the back end, and as you see or have heard in some of the slides, will usurp the timing engine that's used in this SysML with its own event-based timing system. So basically what that means is we no longer have to sit there if we have 4 hours of in-simulation time for 4 hours of reality to let the simulation play out. The event-based timer will allow certain periods of time where there are no events, such as detection, to kind of be jumped forward or skipped over, so we no longer are using time on events that are of less interest or don't really have any pertinence to the mission, of course as modeled by the user. So what I'm going to go ahead and do is click on the run button of this scenario here. And what we're going to see now is we're going to have Cameo now communicate with SDK, and it will load up the scenario of SDK that has all of the entities that we've described. Okay? And there's SDK. And we'll just give it a moment here. And as it's starting up, one thing to note is there is a lot of flexibility in what you can do with SDK and Moxie. For example, if you are familiar with any of the programming interface of SDK and familiarized with how to kind of automate your scripts, one thing you'll note is essentially SDK is communicating with Moxie through the same types of programming languages of object model. But here we can start seeing the demonstration run. Unfortunately, I only have one screen, so we're going to take a look at this demo a few times. But here you can see in the top left, we kind of have this fog of war type of window where the hypersonic vehicle is only displaying what it knows about, which is in this case the target ship and itself. But here you could see that without us telling it, it is going through its executable architectures and now going through the whole radar warning receiver and evasion decision trees, or rather state machines, to determine how to best avoid this target. So for example, if we were to take a look at Moxie, you could see here that now certain parts of the state machines are glowing green and red, or rather in Cameo, are glowing green and red depending on what's occurring due to Moxie. One thing I can also do is stop the simulation mid-run. And now if we take a look, you can see here that I can completely control this SDK interface to take a look at what's going on and maybe kind of take a closer look in case you see something suspicious come up as you're sitting there running your scenario. The advantage of also doing this is, let's say we did have this combined with some parametric analyses where we're doing Monte Carlo analyses, where for example we're changing maybe the aggressiveness of the evasion. And you may find out that on one of the runs, you're seeing a type of emergent behavior or something different than the rest. Well, the advantage of pausing Moxie or pausing the simulation run allows me to save this scenario off as almost a behavioral snapshot that I could investigate at a later time. So we aren't just locked into that specific use case and have to wait for all of this parametric runs or the entire Moxie run to finish. We can have specific save points just by pausing the simulation and allowing it to go. One thing I would also like to point out is, while we're on this page, and I'm going to rerun this again so we can take a closer look at it in a bit, is this current and immediate section up front. So, of course, it already occurred, but one thing that you'll know in a little bit is how quickly that our UAV jumps from this particular section to this first turn. And that's because of what I mentioned earlier with the event-based kind of approach. Moxie could recognize that within this first kind of fly straight section, there wasn't any event of interest. So Moxie was able to essentially go forward in time to this very first critical event where the radar or the hypersonic vehicle's detection was able to sense that there was some type of entity that it had to start avoiding. Okay? So along with that, what we'll do is we'll go right back to Moxie here, or rather Cameo that has Moxie in it, and we'll just let the simulation finish up its run here. Okay? So we're going to go ahead and hit play, and we'll go right back to our hypersonic. And you can still see that I have complete control, and it resumes like normal, as if nothing was to be affected just by hitting pause and play, which is really, really advantageous here for us. Okay? And it's going on with its kind of analyses here. And now you can see it's starting to kind of start its descent as it realizes it's kind of out of the risk area of the ship. And now it will make its way towards the target vehicle here. Okay, and there it goes with the strike. And you can see that this entire route was not planned by us. We didn't, explicitly really model this. So now if we take a look here, we can see that the simulation has completed successfully. We could save off this run and so forth. One other thing I would like to point out is when I did pause, what I also have the ability to do is I can go ahead and add in certain breakpoints in my simulation where I can then change certain values on the fly almost. So essentially I could, for example, pause the simulation, and I see here that there's this type of heading change that's for 90 degrees of a bank angle. Well, I could pause it and instead change this value to something else such that it would then be able to update on the fly as we're going along with the mission. Okay? Another advantage of leveraging Moxie is we can also have in human-in-the-loop types of events in the executable architectures. Now, these could be things such as human error by adding in some type of random noise generation. It could be a type of reaction time that you could add in by some type of delay, and things of that nature to really add that type of realism you would need in your scenario to really show the benefit of having this simulation tool and behavioral modeling in your operational environment. Right? We're trying to use these behavioral executable architectures to sort of observe the operational environment and mission from a perspective that we may not have thought of before, that may lead us finding certain emergent behaviors that were not expected before, which could, benefit us or make us go back to the drawing board in the grand scheme of things. So as I'm going to go ahead and rerun this, really the last thing I wanted to just highlight on was that event-based type of approach, which can really save a lot of time during analyses. So this time we're going to make sure that we're looking at STK the entire time Moxie is up and running. So here we go. We have it kind of built up here. And I think it's very critical because, yes, in this use case, it's very simplistic, but you can imagine that if you do have flights or any type of simulation that may have certain gaps that are due to just traveling between points, it could be just coordinating certain events. You may not want to have the simulation running for that entirety, as it may not be as beneficial from a time perspective. So here we could see the start of the simulation going, and immediately you could see it jumping. So we immediately were able to fast forward a certain amount of time ahead, so we didn't really even have to encounter that. And I wasn't able to pay attention up here, but I'm almost certain it was able to jump a certain amount of like 18 minutes or 15 minutes or something like that. But once again, it's really what separates this from the rest of the tools, and this is just a quick overview to show kind of the capabilities that Moxie can bring to the table. Now, like I was saying, it currently works with Cameo Systems Modeler, but Moxie is made to be used with SDK and a variety of SysML tools going forward. This is just the first iteration, and I hope you look forward to seeing what else we have to come out with Moxie as we progress in the future. Thanks, and take care.